Okay, can I move this bar somehow? Oh, okay. This is the title of today's talk. It's quite long, but yes, it's about EF21-P and Friends, improved theoretical communication complexity for distributed optimization with bidirectional compression. Okay, so this is a joint work with Alexander Turin and Professor Peter Tarik at KAUST. And sorry, here's the outline of today's talk. So first, I will introduce the whole topic of distributed optimization, and I will try to give you a walk through all the main motivations for distributed optimization, and also give you the main problems in the area. So we'll first look how things work for a vanilla version of gradient descent, and there we'll identify some problems and see how the error feedback deals with those problems. And also in this error feedback section, we'll have a look at EF21-P, which is one of the things we created this research project. And we'll see how this EF21-P method can be useful to solve some of the issues we encountered in distributed optimization. And towards the end of the presentation, I will give some primer of other results we have in our paper. So first, what is distributed optimization and why do we actually need it? So modern machine learning models are trained on data sets of enormous sizes. And some of the most successful models are very over-parameterized, meaning that the number of data points is even smaller than the number of parameters. And now we have some problem because we want to train this model effectively, efficiently, but the number of data points is so large that we cannot do it on one device. And one solution to this problem is just splitting the data sets. So we partition it into several smaller data sets and train the model on several devices. This can be computers, mobile phones, or any other kinds of machines. So some central server, and we have some number of devices, and we just do some calculations of those devices and then send the results to the server, do calculations of the server, and send them back. And also, alternatively, we can get to the same, sort of set up the same graph. If we want to, for example, train a model using data from, for example, mobile phones. So we can have millions of mobile phones, and we want to use the data on those mobile phones to train a model which uses the data from all of these devices. And hence we arrive at the following optimization problem. So this is just a finite sum problem, which is very common in machine learning. We have workers, nodes, machines, clients, whatever you want to call them. D is the number of parameters, so the dimensionality of our problem. And now the functions at I will be the loss of those local data sets stored on device I. And we'll later assume that these are smooth and possibly non-convex functions. As I've already mentioned, these are the functions at I. They correspond to some n different machines. And yes, then we want to solve this optimization problem somehow. So let's first have a look how this process works for a vanilla version of gradient descent. We will need the following assumptions. So first, we'll assume that the function f is L smooth, so that this inequality holds, and we'll also assume for now that the function f is mu strongly convex. And these are the sort of classic assumptions under which a gradient descent is usually analyzed. And this is what it looks like in its distributed version. So of course, this is the standard version of gradient descent. And since we assume that f is this average of functions of the fi's, then the gradient of f is just the average of those individual gradients. And now a classic result said that when our assumptions are introduced on previous slide hold, then our algorithm converges after this number of iterations. And this will be needed later. So as we can see, we need to average those gradients, and each of these individual functions of I correspond to different machines, right? To different devices. And to perform actually the gradient step, so that to make this calculation, we need to use the data from all of those devices. So there is need to communicate somehow. That's why we had this graph with the central server, because the devices will be sending those gradients, and then the server will sort of orchestrate the work of all of these devices so that we can perform this step. Okay, so this is more or less what it looks like for gradient descent. So in the distributed setting, we would require first the devices to calculate the gradients at time t, and then the devices send those gradients to the central server. Then the server performs some calculations. So in this case, it just takes the average of those gradients, and it either sends back this average to the devices or updates the model and then sends the whole model. And this doesn't really matter because we obtain the same method, and it's analyzed in exactly the same way. And now these are the two most critical steps in this whole procedure, because it turns out that actually the speed of the calculations, so the speed at which we can calculate the gradients and the speed at which we can average them on the server, is typically much faster than the operation of sending those messages back and forth from devices to the server. And this is the main bottleneck in this distributed setting. And that's the problem that we will be trying to solve somehow. So the first idea, the most natural one, would be to somehow compress those messages. And this is represented by this operator. So the idea is to somehow do something about those large d-dimensional vectors, for example, to sparsify them or do any other operation of this kind, to make it just easier and faster to communicate between the devices and the server. And now there are the two main things one could consider the compression, applying compression operator to. So we can either compress the gradients, or we can compress the models, which will be then sent back the other direction. Or of course, we can also compress both. But first, we will consider just the case of compressing the gradients, because in practice, it's often the case that the speed of uploading information from the devices is slower than downloading them, so that the operation of sending those messages from the devices to the server is typically slower than doing it the other way around. And that's where we arrived at this compressed version of gradient descent. So maybe I'll stop now and ask if you have any questions to anything I've said so far. Okay. So now, what are these compression operators? So the literature distinguishes two main kinds of compressors. So the first one will be unbiased compressors, and the second one will be biased compressors. So unbiased compressors are just some stochastic mappings which map vectors from RD to RD, so that, as the name suggests, the result is unbiased. And also it satisfies this bound on the variance. And biased compressors satisfy a similar kind of inequality, but here, of course, we do not require the equality which gives us unbiasedness. And also, in this case, the compression is between 0 and 1. And two canonical examples of these operators are rank K compressor, which is unbiased, and top K compressor, which represents the biased compressors. So what is this compressor? By the way, in the top right corner, there is the definition, just to remind you in case it's needed. So rank K compressor just samples K random entries from the vector we're trying to compress, and then zeroes out the remaining entries, and also we apply some scaling so that the unbiasedness is preserved. So for example, here we have an example of rank 1 compressor. So we just sample one entry, in this case with example 2. We zero out the rest and then scale by d over k, where d is the dimensionality of this vector and k is 1 in this case. We took it to be 1. So applying rank k compressor to this vector will give us this result. And then the top k compressor preserves the k largest entries, where largest means largest in absolute value, and then zeroes out all the remaining entries. So in this case, the largest entry will be -8. And now in practice, it turns out that those greedy biased compressors tend to work better usually. And intuitively, it may be because they in some way preserve more energy or more information of the vector we are trying to send. Because we don't just send some random entry, but really the largest one. So in some sense, it may somehow preserve more information. But in fact, we do not really have a very convincing theory why it would be the case. But this is what people observed. So now a natural way to deal with the distributed version of gradient descent would be just to, instead of sending the whole gradient, would be to just apply this biased compressor and send those compressed entries. And well, everything is fine apart from the fact that it doesn't necessarily work. And a naive implementation of this kind of operation may even lead to divergence, and it may diverge exponentially. So, yeah. Yes.
So this is what you're saying. This is what I was thinking. And you have a different names.
Different names. Yes. What do you mean by different names? Sorry.
Or different terminology. This is stochastic gradient.
This is gradient descent. This is gradient descent. Those are exact gradients. Yeah, and here, this is some compression of compressed gradient. So it doesn't necessarily have to be stochastic gradient descent, because I think that in stochastic gradient descent, we assume that the gradient estimators are unbiased. And here, if we apply a biased compression operator, right, then it's not necessarily the case that it's biased. But yeah, this is some gradient estimator, and we just want to somehow make this method work. Any other questions? Okay. Okay, I've mentioned that it may not work, it may diverge exponentially. And then in 2014, there was a paper by Said and collaborators who proposed error feedback technique. which is some kind of peaks of this divergence. And initially it was just heuristic, so we didn't really have any theoretical explanation for why this worked. And also a few years later, when there were more papers on it trying to explain why this error feedback may solve the issues with divergence, the theory was not really convincing because it relied on very strong assumptions, like, for example, bounded gradients or homogeneity of the data sets. And also some methods analyze only the single node case, which is not really what we need, because what we need to do is we want to solve a distributed optimization problem. So it was just not helpful. But then in 2021, Professor Rick Tariq and collaborators came up with a new error feedback mechanism, which resolves all these problems and also provides a better rate, because the earlier techniques gave a rate which was worse than in the case of unbiased compressors. But we may expect to obtain the same rate because it was observed in experiments that this should be the case. So the whole idea of EF21, because that's the name of this error feedback technique, is to use Markov compressors. So this is what Markov compressors do. We have some vectors VT produced by some algorithm, and we want to somehow compress them and to make them easy to communicate. We want to use the bias compressors. So the main motivation for why this would work is the observation that if we manage to create this compressor M, so that the distortion between the compressed vector and the vector itself vanishes as t goes to infinity, then it must be the case that this difference goes to 0. And then if this difference goes to 0, then in fact we obtain that the compressed version of the vector gets closer to the vector itself, because well, we can subtract VT plus 1 from both sides of this equation. And then on the right-hand side, we can just apply this inequality, which is the definition of biased compressor. So we see that in the norm, if we put it in the Euclidean norm, then on this side we'll have VT plus 1 minus M of VT minus the same thing. So we can bound it by 1 minus alpha and this thing in a norm. And also, we already assumed, we are hoping for that the difference will go to 0. And if this difference goes to 0, then we'll get that indeed the compressed version of the vector gets closer and closer to the vector itself. And okay, this is the definition of a Markov compressor, but now we want to use it in our distributed learning setup. So to do this, we just substitute for those V's the gradients. So we put the gradients in there. This is just exactly the same thing, but with VT substituted with gradients. And well, the notation is getting quite heavy, so we just define those compressed gradients to be GP. And this is the method we obtain. And what we want to do then is just to use this sequence GT as a sequence of our gradient estimators. Yes.
So the basic idea, the basic idea behind the stochastic gradient was not to compute the full gradient. So just something. But here you need to compute the full gradient, but also function.
Yes, yes. Yes, okay, so maybe I didn't really state it very clearly, but here we will be computing the whole gradients. And what we want to solve is we want to solve this communication issue. So for now, we don't really worry about the fact whether or not it's easy to compute the gradient itself, because the issue we're trying to solve is this issue of communication. And also, I can mention then that later on, we will see that we do the same thing with stochastic gradients. But to introduce the technique, it's just easier to introduce it with the whole gradients because it makes the presentation a bit clearer. Okay, and yes, so we will use those GTs as gradient estimators. And since we are hoping for those GTs to converge to the thing we're trying to compress, this would mean then that GTs will get closer and closer to the true gradients. So that's what we do. This is the first line is just the normal gradient descent with this GT gradient estimator substituted in the place where the gradients should be. And here's our EF21 update of those estimators. But this is of course the single node setting. So here we assume that we have just one device, but it easily extends to several devices. We just do a very similar thing to what normal gradient descent is. So instead of taking this compressed version of the gradient, we take average of those individual gradients. Also error corrected with this GIT. And then they prove that under the assumption that Fi are Li smooth and that the whole function is lower bounded, we indeed get this desirable 1/3 rate. Okay, and this whole introduction of error feedback and so on was because our methods rely on a very similar idea and they are inspired by this. So this is where we get to one thing which was introduced in our paper, which is EF21-P. And now we will again be solving the one node problem here, and this is because we will use this method later to compress the messages sent from the server to the nodes. So there is just one node anyway, because we have one server. So yes, we want to use this optimization problem, and we will do it in a very analogous way to what EF21 did. But here, what we do is rather than compressing the gradients, we'll be compressing the model itself. So a vast majority of papers concerning error feedback compresses the gradients because it's just maybe, I don't know, maybe it's more natural to compress the gradients. But what we do is compressing the model instead. So as you can see, this is essentially the same method, but instead of the gradients and gradient estimator, we have the model parameters and some compressed version of those model parameters. And in our paper, we proved that this method, for this method, both x's and w's converge at this rate. Okay, and it turns out that this EF21-P method is actually a reparameterization of the classical error feedback mechanism, which was proposed in 2014. We just take ET to be the difference between the true model and our complete version of the model, and we obtain this, which is exactly the error feedback mechanism. But now, all our algorithms we develop later explicitly will be using those XTs. So this reparameterization is really crucial and essential in analysis of our algorithm, because error feedback does not even state explicitly those X iterates. Okay, so now let's get to some more advanced algorithms. We'll first consider the convex setting. Okay, but first let's recall what happens in this vanilla gradient descent setting. So this is the reminder of what the method looks like. And again, we are sending the gradients from worker to server, and then server performs calculations and send back the model parameters. And now those vectors are d-dimensional. So the overall communication complexity will be d times this guy, which was introduced in that theorem a few slides back. So we maybe first the definition of what communication complexity is. So it will be proportional to the number of coordinates which are communicated to make our method converge. So in this case, we send the whole d-dimensional vectors, and we perform this number of iterations. So the overall communication complexity will be just d times this complexity. And yes, this is quite important thing here, because we'll be then comparing this communication complexity with complexity of our algorithms and also other algorithms. But yes, it will be stated on the slides anyways. Okay, but now, as we've already mentioned, what we really want to do is we want to compress those vectors, because it may be impossible to communicate the whole gradient. And first, we'll consider just compressing the vectors sent from the devices to the server for the reasons I mentioned at the beginning of this talk. And well, this is quite a popular way to solve this problem, and there are many papers which consider this setting. But we will now have a look at one particular example, which is DIANA. And yes, for this we'll need two additional assumptions which are specific to this distributed setting, because so far we only assumed L smoothness and mu convexity of the overall F function. So now we'll also need Li smoothness of those individual Fi's, and also we'll assume that those Fi's will be convex, and here this will be all Fi's. Okay, so this is the complexity of this DIANA method. And now I will show that the DIANA method can achieve communication complexity better than gradient descent. So for simplicity, we'll use the rand K compressor, which maybe we'll find what it does. So it preserves the K random entries of the vector we are trying to compress, and then zeroes out all the remaining entries, and also rescales so that the result is unbiased. So what we do here is we are sending K coordinates of each vector, because that's what rand K does, and we multiply this by this complexity, and so this is just the overall communication complexity we obtain. But now, since we are using a rand K compressor, it can be easily shown that in this case, this omega parameter, which is the compression parameter for the definition, will be d over k minus 1. And what we do here is we are just substituting this value into this complexity. Then we use the fact that the maximum of Li smoothness constants is less or equal to NL. And what we get here when we perform the calculations it turns out that this is the gradient descent complexity. So indeed, using those compression operators when communicating messages from the workers to the server, we can achieve communication complexity which will be better than gradient descent. Okay, but DIANA assumed that what the hard part of the problem is compressing messages, sending messages from the devices to the server. But it assumed that sending messages back is just free. So we didn't really take care of the problem of what to do with, with sending messages in the other direction. So this is still a problem. And now a sort of natural solution would be to just apply again some compression operator and send a compressed message back. And here's where we finally get to this bidirectional compression thing. So these are the previous state-of-the-art methods. What we can see here is that those variance parameters, those omegas, are coupled in the sense that there is a multiplicative system, which is not desirable. We would rather want those variance parameters to have an additive effective system. And also, it can be shown that both of these communication complexities are in fact worse than the gradient descent. And that's where we get to our solution. So we propose a new method, which is a mix of this DIANA method by Mishenko and our EF21-P mechanism. And what we can see here is that we indeed managed to decouple those noises coming from two conversion schemes. So that in the end, the overall communication complexity has just an additive additive dependence on those noises rather than a multiplicative one. Okay, and what's more, we'll soon show that, in fact, apart from the fact that we managed to decouple the noises, we also managed to finally achieve a communication complexity which is better than gradient descent. But first, what the algorithm looks like. So, the pseudocode is self-explanatory if you read it carefully, but the main message here is that here is the DIANA part, and here's our EF21 part. So, most importantly, the most important message here is that what we are sending is always a compressed message rather than this whole bidimensional vector. So when sending messages from workers to the server, we send this thing, and in the other direction, we send this thing. So why is that? So let's recall that those WTs are the compressed versions of our model, for example. And at time t+1, the workers already hold those WTs from the previous iteration. So the only thing we had to send in order to update those models is just this pt+1, and pt+1 is this compressed vector. It will be easier to see how those things work on a graph. So as I mentioned, we send from the workers those compressed and error-corrected versions of the gradient, and back we are sending the compressed version of the model itself. And here, we the DIANA algorithm works with unbiased compressors, so those CEDs are unbiased, and EF21-P works with biased, which are represented by CP. Oh, and also maybe I should mention that those P's and D's kinds come from primal and dual, because maybe it will be easier than to follow the whole talk. So dual because, well, the gradients are in dual space, and primal because the models are in the primal space. And now what's important is that in some sense, the family of biased compressors is wider than the family of unbiased compressors, because when we scale an unbiased compressor appropriately, we get a biased one. So our method, in some sense, is more general. In some sense, it supports a more general family of compressors. And now, as promised, I will show that the communication complexity is better than the communication complexity of gradient descent. So again, for simplicity, we will use top K in server to workers communication and run K in workers to server communication. So the first one is biased and the second one is unbiased. And this is the complexity we had in the table before. And at each iteration, we send K coordinates. So the overall complexity will be just this. And substituting omega and alpha into this complexity, we again get, using the fact that the maximum LIs is smaller or equal to NL, that is less or equal to this thing. And this is just the complexity of gradient descent. So we indeed get that the communication complexity of EF21 plus DIANA is no worse than gradient descent. But maybe no worse is not really impressive. So how much better can it be? Our analysis considers the worst case scenario for those compression parameter alpha and Li smoothness constants. But in fact, it's the case that the effective alpha, meaning the alpha we see when doing experiments, is much larger than the theoretical thing, and also L max is anywhere between L and NL, and usually it's in fact much smaller than NL. So we see that the improvement can be massive, right? Because N is the number of machines, so it can be millions, right? And yes, in fact, as far as we know, this is the first method which uses bidirectional compression, which is no worse than gradient descent in this sense. And also the first method to decouple the noises coming from compression from servers to worker and from workers to server. And we won't really have time to go over all the details, but what else we show in the paper is we analyze this algorithm with stochastic gradients as well. This gives us the same convergence rate apart from this statistical factor, which we does not depend on alpha, which is the compression constant. And also we analyze another method with bidirectional compression, which is EF21-P plus DCPD, which is also some mix of EF21 primal and other methods which compresses in the other direction. And we obtain even better convergence rate, but this is under the assumption that we have the interpolation grading, which in fact is very common in machine learning models, which are usually heavily over-parameterized. And here are some experiments. The left graph shows how the function value decreases as the number of bits sent from workers to server increases. And here we have the same graph, but with communication from server to workers. So what we see in the left graph, the blue line is the DIANA method. So this is just the method which was compressing only in one direction, the method we were starting with. And what we see is that EF21-P plus DIANA does not really improve anything, but this was as expected because the methods do the same thing when sending gradients from worker to server. But what we see in the right graph is that when sending messages from server to workers, the improvement is really massive because the x-axis is on log scale. So this is in fact 10 to the power 7, and here's 10 to the power 10. So we get roughly 1,000 times less bits in this case. Oh, and also the red line represents this other algorithm, which we really won't have time to analyze. But yes, it can be better in practice. And now a quick primer on other methods we also have in the paper, because what we've seen so far was the convex case, but we also analyzed the non-convex case where we need the analysis of a new method, EF21-P plus the CGD. So this method also is the first one to decouple the noises coming from different compression schemes, similarly as in the convex case. And it gives us new state-of-the-art convergence rate in the low accuracy regime. And also we give some examples of optimization problems where this new method is better than previous state-of-the-art methods, even in the high accuracy regime. We also analyzed this method under several additional assumptions like strong row, and also in the homogeneous regime. The most important thing is that we do get improved rates, and we're also better than other methods which deal with the same problem. And actually, all of those results in non-convex case are just a result of our unified analysis framework. So these are all corollaries of our analysis, which works in this non-convex case, where we use the EF21-P mechanism to compress the vectors sent from server to workers. And yes, that would be the end of my slides. So I would be happy to answer any questions you may have.